Okay, good afternoon. Today we will finish this part of the lecture, still about the friction in the fluid flow. And in our last discussion, we have discussed I have give you this exercise. So have you done this exercise?
Most of the parts, sir.
Okay, maybe in 1 hour, I will try to guide you how to do this exercise. So please prepare like a paper or and also calculator with you to help with the calculation. So basically, this is the application of the Bernoulli, and we will see how the natural gas in this part is because in this case which one? Okay, this one, the natural gas is considered have the molecular weight of 17. Usually, natural gas is a mix between light hydrocarbon and until medium hydrocarbon. Medium means from C1 until around maybe around C12. But since we have the molecular weight of the natural gas is 17, so from our last discussion, we can assume that this natural gas, the closest one is CH4 or methane gas. So I have asked you to find the properties of the methane gas in terms of viscosity. For the density, you can calculate from the gas ideal equation. So if we take down the if we want to visualize the problem, we have Sengkang, right? Sengkang, and the other place is Parepare. You have a different height. So from the exercise, the length from the pipeline is 70 kilometers, and Sengkang is 300 meters above or higher of Parepare. So you can, hope it's okay if I do in this way. So this one is 300 meters, the length, and for this one is 70 kilometers. The natural gas has molecular weight of 17, and then the well production flow rate is 50 mm SCFD. So the production flow rate from the well is 50 mm SCFD. So it's 50 times 10 to the power of 6 cubic feet per day. 50 million standard cubic feet per day. So have you, in order to simplify our calculation, we will use a standard internet SI unit, the standard unit. So you need to convert it into cubic meters per second. Have you done the calculation? How much is
Yes,
50?
sir.
Okay, how much?
So I got it wrong. So
Okay, can
I
somebody else help you to calculate?
yes, sir. So if I change it to meter cube from feet,
Uh-huh.
it's 1415842. That yeah. Itu I haven't changed it to seconds.
Okay, so just divide it by day means like 24 hours times 60 minutes times 60 seconds, right? That's the conversion from day into second. And this one, you convert it into cubic meters. Ada yang sudah menghitung?
I got 16.38, sir. Like as a whole, like the whole thing.
16.3
16.38.
cubic meters a day. Okay. Can somebody else also check the calculation?
I also got the same, sir.
Same. Okay.
Yeah.
Okay. Then uh, you get the this one is the flow rate for the standard condition. Standard mean okay. I think I have tell you the condition that uh, used for calculation of standard. It's 14.73 psi absolute, right? And just a sec. Let me check again. And then
60 degrees Fahrenheit, sir.
yes. So convert it into Pascal and convert it into Celsius. Sorry, Kelvin. How much?
The temperature is 303 degrees, if I'm not wrong. 288, sorry, sir.
288
Yeah,
Kelvin.
288.7, yeah.
0.7. Let's make it 289 then. Okay, 289 Kelvin. And then from 14.73 psi converted into Pascal.
I got 503,317, sir.
Just use a scientific number, number, comma, number times 10 to the power of something.
Wait, sir. Sorry, sir?
Yeah, if there's a lot of thousands, then you can
Okay.
mention it something, comma, something times 10 to the power of.
Okay, sir. So it's 5.0 times 10 to the power of 5, sir. Wait, I think I salah deh, sir. Bentar, sir.
Okay, check again, please. And please, yang lain juga ikut menghitung. PSI.
I salah, sir. It's 1.01 times 10 to the power of 5, sir.
Okay, one. Also around. Okay, it's not that much.
So it's 101 kilopascal, sir, somewhere there.
This one, right?
Yes, sir.
This is 1,000. So this one is titik. Okay. Okay, then you use the current condition. This is the standard condition. Based on the exercise, the current condition is the pressure is 60 and temperature is 30. 60 kilogram force over square centimeters, and the temperature is 30 degrees C. So you needed to convert it first. So the actual condition, the pressure is 60 kilogram force. This one, but this is gauge, right? This one gauge. Be careful. So you need to add the 180 M value, and then the temperature is 30 degrees C. So this one is 303 Kelvin, right?
Also, sir, that's in centimeter square, sir. So we
Yeah.
need to change it to meter square as well.
Oh, you change into Pascal. Just directly change into Pascal and add
Okay.
101,325 Pascal.
If you change it to meter square, that's Pascal, sir. Is that right?
Is it?
I have no idea, sir. That's why I'm asking, sir.
No, because it's different. It's the British unit. It's the kilogram force. You need to add some, I think it's like gravitational value or something. So just find the conversion factor from kilogram force per square centimeters or square meters into Pascal.
I got a really small value, sir. It says 5.884 E plus 6.
5.4
884 E. E.
Oh, it's 10 to the power of 6. E, right? Like this one, right?
Yes, sir.
This one, right?
Yes, sir.
So this is 10 to the power of 6. Have you add 101.325 Pascal?
Sorry, sir. I'm confused, sir.
This one, you got from this one, you got from this one, right?
Yeah.
Yes, right? It's still in the gauge pressure. Remember, if
Oh,
it's in the
yeah.
gauge pressure, you need to add the atmospheric pressure.
180. Yeah.
180 m is around this one, right? So if you convert the actual pressure into absolute pressure with the unit of Pascal, what is the value?
I got 5.98 times 10 to the power of 6, sir.
5.98. Okay, so just add one more. 5.98. Okay, so this is the actual value of pressure and the temperature. And this one is the standard value. And 16.38 is the volumetric, sorry, this is should be per second, right? Okay, sorry. Yeah, this one already met cubic meters per second, right? So the 16.38 cubic meter per second is the volumetric flow rate that has been calculated in this condition for 101.560 Pascal and 289 Kelvin. So you need to know the value of this flow rate when you are measuring in 5.98 times 10 to the power of 6 Pascal and 303 Kelvin. So you are using the, basically you remember the ideal gas, right? P
Yes,
times
sir.
this one. Because this one is always constant. If you just compress or expand the gas, only the pressure, uh, sorry, only the pressure, the volume, and the temperature that will be changed. The mole or the mass will be the same. So you can use,
PV over T, sir.
yes, with the standard condition, you can use the standard condition as the condition number one and the actual condition as the condition number two. And you can replace V1 with the volumetric flow rate. And then V2, you get the actual volumetric flow rate. Okay. One is standard and two is actual. Then you can get the value in cubic meters per second. This one is 16.38 cubic meters per second. How much?
I got 0.29, sir.
0.29. How about the other?
I got the same.
Okay. Okay, so this one is the volumetric flow rate of the actual flow from Sengkang to Parepare. Okay, what is the question? Now, with that flow rate, we want to flow the gas with the length of 70 kilometers, and then the height is 300 meters, this one, and this one, by using three different pipes. Three different pipes mean the pipe have three different diameters. First is 5 inches, the second is 10, and the third one is 15. And the diameters, the pipe will have epsilon over d is 0.002. So what you need to do? What you need to calculate after you finding the flow rate?
Find the velocity that will be used for the EF, sir.
Sure, yes. So you need to find the velocity. Velocity will be, okay, why is this? The velocity will be the flow. How come this? Sorry. Will be the, what happened with this pen? Sorry. Why it always makes lines divided by A? Okay, just a minute. I need to check the setting first. Okay, you need to calculate the velocity by, how do you calculate the velocity?
The volumetric flow rate divided by the area, sir, of the pipe.
Yes, so you need to calculate for each diameter how much is the area. Okay, for the diameters 5 inch. Why it always like this? I don't know. So for 5 inch, what is the area? And then for 10 inch, what is the area? And for the 15 inch, why it's always created? What is the area? Directly in square meters. And then the velocity will be the velocity will be the volumetric flow rate divided by area. How much?
The volumetric flow rate is 0.28 ya, Sir, tadi ya, Sir? Benar nggak sih?
Yes,
Oh,
0.29.
0.29. Okay.
Did you already calculate, right?
Yeah, yeah, yeah. For the inches, you also change it to meters, right, Sir?
Yes. So
Or
change inches into meters and then convert it into area. So the unit will be square meters. And then the velocity is in meter per second. Sorry, I wrong type this one. So the unit will be meter per second.
for U1, it's 22.9, Sir.
Which one? Which one? The
U1,
area
Sir.
or the velocity?
The velocity, Sir.
22.9.
Yeah. Bentar ya, the area.
Then
The area is 0.0127 of 5 inches, Sir.
okay.
The area for 10 inches is 0.05. 0.051, sir. 0.051.
51.
Yes.
Okay. And area for 15 inch?
0.11, sir.
0.11. Okay, so please calculate the velocity, the linear velocity.
For U2, I got 5.68, sir.
5.68. And the third one?
Sir, for the third one, for 15 inch, I got 2.56. Though the decimals may be a bit off.
2.56. This one is it? Okay. Have anyone already calculated the density? The density and the viscosity. The density should be in kilogram per cubic meters and the viscosity should be in Pascal second.
Kalau density-nya I salah, sir, gara-gara I thought kilogram force tinggal digantiin jadi meter square, kan tadi centimeter square.
No, it's
So harus di-calculate. Kalau misalnya viscosity-nya, I cari di Google kan what's the same as CH4.
yes.
Ya, CH4 I get kalau benar nggak sih, sir? 2.33 times 10 to the negative 5?
2 point, let me check. The unit is already 2 point some, how much? For the methane gas? Hello?
Yes, sir. Can it has to be in 30 degrees, sir, if I'm not wrong?
Yeah, it's around 30 degrees.
Uh,
The viscosity, I think it doesn't change much with the temperature. I mean, the data should be, it's around in 25, right?
is it the 1.03, sir?
Yeah, it's around,
Or yeah, 1.03 times 10 to the negative 5. Is that right, sir?
yes, minus 5, right? Okay. And how about the density? Density is using the ideal
PV
gas.
equals nRT, right, sir? Yeah.
Yeah. How much is the density? Oh, for the methane gas is between 20 and 50 is around 1.1. So it should be larger than this one. Around at 20, if I see the table, at 20 is 1.1, at 50 is 1.19. So it's around 1.1. How much is density?
What's the pressure again, sir? The
The pressure,
actual pressure,
the actual pressure,
5.98, right?
yes, 5.98 times 10 to the power of 6.
Also, sir, the MR, since it's 17 is in grams, right? If I'm not wrong. Should we change it to kilograms?
Yes, the MR, IU. 17 in gram per mole. So you should change into kilogram per mole.
I got 40.4, sir.
40.
Yeah, wait, is that right, sir? Because it seems so big.
Yes. The density of the air is 1 kilogram.
0.2. Yeah,
It's around
1.2.
1. So it should be around that. It should be that one.
For the R value, I used 8.31. Is that right, sir? All right. Temperature is in Kelvins, 303.
Yes. It should be less than air, right?
It should be, sir. To the power of 6, right, sir? That's right, right?
Which one?
The pressure is to the power of 6, right?
The pressure. Yes. Based on your calculation, I haven't checked.
Yeah, sir.
Okay, so the density should be m over v, right?
Ada yang salah gitu ya, sir? I still got 40.4, sir.
Is it? Oh yeah. How come it's so big?
Ada yang salah di pressure-nya nggak, sir?
Can somebody check the conversion from this minute? Let me check. Uh, how much is the 60? Okay. Yeah, it's correct. Because the pressure is very high, then the density of the methane, that the density of the gas or the air is around 1 kilogram per cubic meters is the density that has been measured in atmospheric condition, right? So if we increase the pressure and the pressure is 10 to the power of 6, so it's around 10 times of atmospheric pressure. So the volume will be very small. And if the volume will be if the volume is very small, then I think it's okay. The density will be very high. So around this one. Ayo, why? 40.35, right?
Yes, sir.
Okay, yeah, correct. Okay, now you got the value of density, viscosity, velocity, and then the diameters. Don't forget to convert the diameters into meters, right? So you have to calculate Reynolds number. How much is the Reynolds number using each value of velocity and density?
Sir, for the diameter, it's just the diameter of the pipe, right?
Because
You don't have to use the equivalent diameter because it's gas anyway, right, sir?
oh yeah, you don't need because it's already gas, and we gas is always filling the pipe, right?
Yes, sir.
Don't forget to change the diameter value into meter, not in inch, and then use this equation to calculate the Reynolds number. How much is the Reynolds number for each pipe diameters?
Sir, for the Reynolds number for 5 inches, I got 1.06 times 10 to the power of 7, sir.
Okay, please the other students, please recheck the calculation.
I'm sorry, how much did you get?
1.06 times 10 to the power of 7. Is it correct?
I might have done something wrong, sir.
Okay, please the others do the calculation as well.
For the second one, sir,
Mhm.
I got 5.29 times 10 to the 6.
29.
Yes, sir.
Okay, so the Reynolds numbers is increasing. Decreasing, sorry.
For the third one, sir, I get 3.58 times 10 to the 6.
Okay. After you got the Reynolds number, then you find what? Friction factor, right?
Yeah, friction factor, yeah.
So you calculate friction factor for each Reynolds number. How to get the friction factor value?
16 divided by Reynolds number, sir.
This is already turbulent.
Benar juga, sir.
So, okay,
Ha-
I need to remind you that a friction factor is classified. You can calculate by using the 16 divided by the Reynolds number only for laminar. But for turbulence, this is already exactly is already more than turbulent, right? I mean, it's already completely turbulent. Then you can do, you can check the slide.
Pakai E over D, sir, the roughness.
Yes, that's right. So you need to check the this one, and then you can get the friction factor from the graph. The E over D is 2 times 10 to the power of minus 3, right? So it should be above this line. Or since it's already completely turbulent, you can use this equation as well. Because it's already very, very high Reynolds number, then you can use this equation. Okay, please take note this equation and try to calculate the friction factor for each Reynolds number. The epsilon over D is 2 times 10 to the power of minus 3.
For finding friction number 1, sir, I get 5.86 times 10 to the negative 3.
5.86.
86 times 10 to the negative 3. Is that right, sir? It's somewhere there.
I think it's around there. Let me check from the graph. How much is the Reynolds number? The Reynolds number is 10 to the power of 7. So around this line, right? Okay. Dua, tiga, empat, lima.
Wait, did I do it wrong, sir? Did I use the wrong formula?
You can use this one, right?
Yeah. Sir, if you use that one, you don't have to use the finding.
You don't need to use this one.
Yeah, you don't
want
have
to
to use the Reynolds number, right?
Yeah, because it already. So if you see, right, if the Reynolds number is around 10 to the power of minus 7, and the epsilon over d is 2 times 10 to the power of minus 3, the line should be around this one, right? And it's already in the straight line. It means the Reynolds number is not significant anymore. So it's already in the straight line. Then you can use this one. That's the definition of very high Reynolds number. It's the area, or the area when the Reynolds number is already not influencing the Dixon factor, the straight line. I think it's already okay. 2, 3, 4, 5.
Yeah, it's right, sir.
Yeah, it's around this one, right? So it should be okay. You can use the formula. How about the second and the third one?
Sir, if that's the case, wouldn't all the finding friction be the same, sir? Since we don't have to use the Reynolds number anymore.
Yeah, I think should be okay. Yes, correct. That's correct. Because it's already the function of uh, epsilon over d. Okay, then. Any question from other student until this step?
Sir,
Yep.
I am still confused about my Reynolds number because I couldn't get that number that Kevin got. So maybe I'm using a wrong value. I'm not sure, sir.
Use this one, but the density is this one, right? 40.35 is already in standard unit, and then the diameters is this one. You use each of this one, but convert it into meter first, and then the velocity is this one for each number. Oh, okay. Is that answering your question, Gamma?
Oh, I see, sir. All right. Now I see where I got it wrong.
Okay.
All
Oh,
right.
for
Thank you,
Kevin,
sir.
this one, this Reynolds number is 10 to the power of minus 6, 10 to the power of 6, right? So it should be this one, around this area. So it's not in the stable line. I think the value might be slightly different. Although it's not much different. Just try to get from the figures whether the value is still the same.
It's hard to identify those, sir, from the graph.
It's still in the straight line, is it?
Yeah, it's just somewhere there, but it won't be exact, right, sir?
3 times and 5 times, right? Yeah, it's still in the straight line, so it should be okay. So after you get the friction factor, you get to calculate FF, right? For L over D times friction factor times this one. So please calculate EF1, EF2, and EF3. The diameter is different. The velocity is different. Using each of the diameter and each of the velocity. I think it's easier if you calculate in Excel, right? Because it's like step-by-step calculation.
Sir, for EF1, I got 3.27 times 10 to the 6.
3.27.
27 times 10 to the 6.
Okay. The length is 70 kilometers.
So it's 70,000 meters, right, sir?
Yes, correct.
For EF2, I get 1.04 times 10 to the 5, sir.
1.04.
Times 10 to the power of 5, yeah.
Okay.
EF3, sir, I got 1.41 times 10 to the power of 4.
Okay. How about the others? You get the same value until this part. Okay. After you get the value of EF, now you are ready to put it into the Bernoulli equation. Please see again the profile from Sengkang to Parepare. Parepare is lower, right? 300 meters lower, or Sengkang is 300 meters higher. So you can put the Bernoulli equation. It will be, sorry, wrong formula. So because you are calculating EF and the unit is joule per kilogram, so all the Bernoulli should be written in specific energy. Okay. My question now, this is the Bernoulli, and point one is Sengkang. Point two is Parepare. What will be the value of P1? So P1 will be pressure of Sengkang, right? And P2 will be pressure of Parepare, the one that questioned in the exercise. This one. So basically, you need to calculate the, which one? Determine the gas outlet pressure. So it is the pressure at Parepare. So this is the pressure in question. How about P1? Pressure of Sengkang is which
It's
one?
given, sir. The inlet.
This one, right?
Yes.
Okay. Pressure at Sengkang is 5.98 times 10 to the power of 6 Pascal. And then pressure of Parepare is the one that has been asked in the question. Okay, how about this one and this one?
If you put GZ2 into the left side, sir, it will be 300, sir. 300 multiplied by G. Since what's given is the difference, right, sir?
Yes. So, okay. The consensus is one is Sengkang, two is Parepare. We already write this one, right? So, how much is the value of Z1 and how much is the value of Z2?
So Z2 is 0, Z1 is 300.
Okay, you can use Z1 is 300 and Z2 is 0. or Z1 is 0, then Z2 is minus 300. You can choose either of this. Any question about this one? Because the height difference is 300 and Sengkang is higher. So we take higher position as positive value and lower position as negative value. Okay, for this one, I choose the first one. Okay, then Z2 is 0. Then you calculate G times Z1. Don't forget, it still have G value. Okay, how about velocity 1 and velocity 2? Is it the value from here? Or is it not?
I think U1 would be the velocity on top, sir.
Sorry.
U1, the
Mhm.
one from Sengkang, would be the one that we have, the one on top.
The one at 22.9, is it?
Yes, sir.
Okay, and velocity at point 2?
I'll make
At
a
pare
guess
pare.
that it's 0, sir.
Why 0? Then it's not flowing, right? If it is 0.
I don't know, sir.
Okay, now you have the gas flow rate is, how much is the value? 0.29, right? Cubic meters per second. That's the flow rate of the gas. It means throughout the whole line from Sengkang to Parepare, the volumetric flow rate is 0.29 cubic meters per second. Understand, right? Because it's the conversion law, mass conservation law. I hope you still remember. Ya.
Yes, sir.
Selama perjalanannya, kecepatan alirnya itu tetap 0,29 meter kubik per second. Kecepatan air dari hukum kekekalan massa from the mass conversion law. And then, for example, you choose pipe with the diameter of 5 inch. The first diameters. From Sengkang to Parepare, is there any change in the diameter?
No, sir.
No. So if you choose one diameters, it means throughout the flow, throughout the journey from Sengkang to Parepare, then the pipe has one value of diameters. One value diameters means one value of area. It means one value of velocity, right? So
Yes,
throughout
sir.
the journey, the velocity is constant as well, because the pipe only have one diameters. The diameter of the pipe is not changing. For one case diameters, right? Suppose you choose the first diameters, then the velocity throughout the journey is 22.9. It means U1 and U2 is the same, right? In the Bernoulli equation. This one and this one is the same. The velocity is constant. So it's cancel out each other. Paham ya? Understand?
Understand, sir.
So it's not the U1 is 22.9 and then U2 is 5.6. No. For each diameters, then the velocity is the same. Same between Sengkang and Parepare. Then you can solve the P2. So for P2 for pipe diameter 1 is how much? P2 for pipe diameter 2 is how much? And P2 for pipe diameter 3 is how much? Please calculate using this Bernoulli equation. All in Pascal.
Sir, do you want G in 9.8 or 10, sir?
G 9.8 lah.
Okay, sir.
The density, you get the value, right? 40.35. EF, you get the value of each EF from each diameter. Then you can calculate the pressure. P2 is pressure at pare-pare, comma 1 means for the diameter 1, for the diameter 2, and for the diameter 3, using each of EF.
Sir, the difference in height, is it in meters, sir?
In meter, it's already in meter.
All right.
Yeah, it's already meters.
Sir, I got a negative value, sir.
Yeah, it's fine.
Is that right, sir? If I get a negative value, wouldn't it be like back pressure, sir? So backflow or something?
Yeah, I'll explain to you later. Just give me the number for all the three pressure.
Okay, sir. So for the first diameter, using the first diameter, I got negative 1.26 times 10 to the 8, sir.
Okay.
Sir, for number 2, I got 1.9 times
Minus,
10 to the 6.
okay, minus, is it?
Not minus, sir. For the second one, it isn't minus.
Are you sure?
Yes. Bentar ya, I cek lagi, sir. Mungkin salah.
Please, others confirm, recheck the calculation as well.
I
So
got the
the
same as
one
Kevin, sir.
the one that's different is just the EF, sir.
Yes.
Yeah. So yeah,
And
I
the
got
EF
this.
is not changing so much, right? I think. Okay, okay, okay. This one is 10 to power 5 and it's 10 to power 4. Okay, okay. Can you repeat again the number?
1.9 times 10 to the power of 6, sir.
Okay.
Sir, for the third one, I
Mhm.
got a 5.52 times 10 to the power of 6.
Okay. Positive as well.
Yes, sir.
Okay, how about the other student? Is it the same?
I got the same, sir.
Okay. Okay, so P1 is how much? 5.98, right?
Yes, sir.
Okay. So from the by choosing, I mean the well production rate or the gas flow rate, the volumetric flow rate is the same, right? 0.29 cubic meters per second. Then by changing the pipe diameters 5, 10, and 15, you got the pressure at pare-pare at the end point. For the first diameter for 5 inches, you found out that the pressure is minus. What is the minus means? The pressure at point 1 at Sengkang is positive, right? And then pressure at pare-pare is negative. It means somewhere in between, the pressure is 0, right? So when the fluid has pressure 0, what will happen?
Static, sir.
Static, or it means it doesn't flow anymore. It means when you choose the pipe with 5 inches diameters, then you got nothing in pare-pare. There will be no gas flow in pare-pare. How about the effect of increasing the diameters? By increasing the diameters, you found out that the pressure at pare-pare is increasing, right? At the 10-inch diameters, it's 1.9, and at 15 inches, it's 5.52. Okay, what can you say about these two? It's still flowing, right? It means you still have gas in pare-pare. It's assuming your calculation is correct, but the trend should be okay. It should be increasing. The pressure should be increasing because the EF is decreasing, right? It means when you increase the pipe diameters with the same roughness, you got decreasing value of EF. It means the energy that lost into the environment is much, much lower when you are using higher diameter. And you got higher pressure at the end. This is more preferable, right? Higher pressure at the end is preferable. Why? Because you can still add some devices or add some arrangement at the end point in order to treat the gas because it still got some pressure. How about the first one? Since it's already minus, it means at somewhere in between the pressure is already 0, that you need to add something to add the energy that has been lost. That's why you need a blower is for smaller pressure increase, or you need compressor. That's why we will discuss blower and compressor after this lecture. But for the second and the third diameters, you do not need the compressor. Even in the third diameters, it means you still have quite pressure at pare-pare. Ya, jadi tekanan because the initial pressure is 5.98, right? And then in pare-pare you still have 5.52. So it's a small decrement of pressure. This one is more preferable. Okay, but what is the trade-off? What is the differences between pipe with the diameters of 10 and the diameters of 15? Which one is more expensive?
15, sir.
Yeah, because you need more materials, right?
Yes, sir.
Even if the length is 70 kilometers, right? So it's that's the trade-off. For the higher diameters, you can get higher pressure at endpoint, but the trade-off, you need more capital value to build the pipeline, more investment to build the pipeline. Kira-kira begitu ya? Smaller diameters means cheaper pipe cost, right? But it will lead into higher pressure drops. it will lead into unit compression. Okay, any question?
Understood, sir.
Okay. Is there any other question for other student from other student? Okay, if not,
For me,
then
no,
yes.
sir.
Yep. Yes, Alisa, do you want to ask something?
No. For me, I have.
Okay. Okay, then today or this part of the lecture will be my last lecture for the second part of the fluid mechanics. Starting from Thursday, or I think Pak Anggit already rearranged the class. The materials will be delivered by Pak Anggit, and I will see you again after the second exam. Okay, thank you very much and good afternoon.